Hello. How's everybody doing?
Good.
Hello, Professor. I'm good.
Good. So you guys are all like you would have joined college in 2021 or 2022 or even 2023, right? You were in school when COVID hit, correct? In high school.
Yes.
Yeah, all this online teaching brings back memories of COVID. I don't know how many of you remember. Okay, so we'll get started. It's 11:20. I'm recording this session. Um, I would really appreciate if you have a camera, if you could turn on your camera so that I can have some conversation, at least some faces to look at. So last lecture, we wrapped up introduction or chapter one. We had a three-lecture discussion on what is a fluid. We contrasted that with a solid. And then the one of the things that I kept insisting upon is fluid is not a noun. It's not any particular material. If a fluid, the word is an adjective or the description of the phase in which the molecules are subject to pressure, temperature, and shear stress, depending on those. The same material can exist as a fluid, the same material can exist as a solid or something in between. We saw that with numerous examples like ice, water, and steam. You can have liquid nitrogen, you can have gaseous nitrogen, you can have solid carbon dioxide, liquid carbon dioxide, or gaseous form. You can have lava flows, which is usually rock, which is rock solid, but rock can also flow. That is what lava is. We also saw what is called as the Knudsen number, which is a comparison between the average distance traveled by the molecules to the length scale that we are concerned in. And typically in mechanical engineering applications or in this course, we work with Knudsen number being very small, such that the mean free path, which is of the order of about 66 nanometers, is much larger than the length scale, which could be a few millimeters, few centimeters, few meters, or even larger structures. We also saw we also had a discussion about units and dimensions. We talked about how to write the dimensions in terms of mass, length, and time, and temperature for many basic quantities. If at all any question comes from this unit, there could be one on dimensions, like asking you to write out the dimensions of energy or specific heat or pressure or some other quantities that we commonly encounter. One practice I strongly recommend is whenever you encounter a new quantity, take a moment to figure out what are its dimensions and what is the unit. When I say pressure is measured in Pascal, you should be able to say how much is or what is 1 Pascal in terms of the other quantities like kilogram, meters, and second or MLT. Okay. We also saw, I had a discussion about fluid properties. We talked about density, ideal gas law, when it is valid, and then viscosity, bulk modulus, vapor pressure. These are all discussions we had in the class. I didn't have time to talk about surface tension, so I asked you to look at it yourself. So I hope you do that. Okay. So before we start the next unit or next chapter on fluid statics, any questions, anything that you want to say, ask at this point? Sorry. No? Can I take everything is very clear that you don't have any questions or confusions? All good? Okay. Sorry. Okay. I can't make you talk, but I would strongly urge you to be a little curious about not only the course and the grades and everything, but also about fluid mechanics and try to observe it in the real world. As we speak, there's a lot of snow out there, so there is a fluid phenomenon that you can observe if you care to see. So do spend some time in the snow trying to think about things. Okay. All right. Fluid statics. Where do we begin? You've all taken statics. You are all masters of the structures that don't move. Okay. So when we talk about fluid statics, what are we discussing here? We are talking about a fluid that is at rest. It's not moving. So we did talk about it. Just because a fluid is at rest, does it mean the molecules are at rest or molecules are not moving? So you have a fluid, could be, let's say, a liquid, and this liquid is not moving anywhere. It's not flowing. There is no shear. And what does that mean? The molecules that are going around, they have their random motion. They have all kinds of velocities in every possible direction and magnitude, but they have roughly statistically in equal and opposite numbers, so that the fluid as a whole is at rest, but the molecules are in constant motion. So the fluid is at rest. The molecules are in constant random motion that cancels each other. Okay. So the first question we want to ask is, in this fluid, what is the nature of pressure at a point? So if I were to stick my finger in here, or stick literally a sharp stick in here, what would this tip feel? What is going to happen at the tip? So if I draw that a little bit magnified, let's say I have a surface. It could be a temperature sensor, or it could be a pressure transducer. It could be some kind of sensor or my own finger. If I zoom in what's going on here, what would that picture look like? Can you talk, please?
Would it be molecules colliding with that tip?
Correct. So molecules are randomly bumping onto this. They are smacking it, transferring some momentum, and they are essentially pushing this surface. So if you place any arbitrary surface, you can think that there are molecules that are impinging on one part of the surface, and statistically true, it should also be true that there are molecules on the other part giving more or less the equal kick. Okay. So the first question I want to pose is that, is there a directional preference to pressure? Meaning, is the pressure same in every direction, or will it have different values in each direction at a point? Is it radially symmetric, or is it having some kind of a directional dependence? That's the question. Intuitively, what do you think? So you put a measurement instrument or a finger or some kind of surface into the fluid. One thing you could agree is there is no motion of this fluid, so there is no preferred direction. The molecular motion is just random. So if you insert a surface, that surface is going to hit by molecules the same way from every direction. There is no real preferred direction here. So the first insight that we are kind of taking from that basic idea is that pressure is a scalar at a point. It has the same value or a single value in every direction. There is no components. There is no XYZ dependence. It's just a single value pressure at a point. Okay. Is that connecting with you, that if I say that there is no directional dependence, do you understand that, or you would like me to use a slightly different term or a simpler term? Yes, no. If it is no, please tell me so that I can try something else. Okay, since nobody is willing to talk, I take that as you are okay with it. Because see, this whole thing will work only if you tell me what is not landing well or working out for you. Because you are the one who is trying to learn. I'm the one trying to show you how things are or teach. If you don't say anything, what am I supposed to assume? Is it a yes that you get it, or is it a no that you just don't want to say something?
I mean, I think that definition makes sense.
This is all I asked for. So that if it doesn't make sense, that's fine. But I want somebody to talk, please. Okay. But otherwise, I am having a really hard time. I have like what, 12 names on my screen, not even your face if you are in class. It's very hard to know if something is landing or not. That's why I asked if anybody could come on with your camera on. So thank you. So section 2.1. Okay. The book has a short derivation about how pressure is a scalar. I choose to skip that derivation because I feel that derivation is very made up and kind of artificially made to work. But the more intuitive way to saying that pressure is a scalar is that molecular motion is random, inserting a surface at an arbitrary orientation into a fluid, gives the surface no net force, because statistically the surface receives the same impacts or momenta from the molecules. If the orientation is arbitrary, it means every direction is the same and there is no preference. And that's why pressure is a scalar. Okay, so we usually use the letter lowercase p to denote pressure. And as we'll see later, pressure for liquids is slightly different for pressure for gases because of compressibility. We'll get to that. Okay, so that's section 2.1. Section 2.2. Okay, 2.2. We talk about a basic equation for pressure field. So pressure at a point, okay, that is a single value. We talk about, sorry, pressure at a point. Pressure, I should say, at a point is a scalar P. When we talk about pressure field, what we are talking about is P, the pressure, as a function of position or space. Like it could be at different points, and those points we can, let's say, denote by their coordinates X, Y, and Z. Everybody knows Cartesian coordinates, right? Even if not entire vector algebra, at least you have heard of X, Y, and Z coordinates. So I'm assuming that. Is that okay?
Yes.
Okay.
Yeah.
Thank you. Okay. So we'll just keep it simple and have a XYZ coordinate system. XYZ. All I'm saying is the pressure can vary from point to point, and that pressure field is a function that assumes values at different points, and those points are defined by their coordinates X, Y, and Z. Okay. So we want to ask the question, how does pressure vary in a fluid? Okay, that is the question we are trying to ask. Now, the first thing we want to declare at the beginning is that let's assume that this fluid is subject to forces, but not shear forces, or but not experiencing internal shear force or stress. This is an important point, which the book actually kind of doesn't explain better, I would say. It just says, oh, let's consider, I'll read it from the book here. Although we have answered the basic question of how the pressure at a point varies with direction, we are now faced with an equally important question. How does the pressure in a fluid in which there are no shear stresses vary from point to point? It kind of says, let's consider no shear stresses. But what does it mean actually to not have shear stresses? What does it mean to have no shear stresses? That's an important question because I want you to now think about first shear stress, okay, and its relation to the fluid velocity and viscosity. In the previous unit, we saw the definition for viscosity. Anybody remembers that or can recall that or have revised in their when they were studying? What is the relationship between, let's say, shear stress and fluid velocity? I'm going to draw a picture to help you refresh because this is an important part of this whole course. So here is a fluid. Let's say the top layer is being subject to a shear stress and it's moving at a certain velocity u. And as a result, the subsequent layers get dragged on. We talked about that. So what you have is a velocity field which develops. Sorry, 1 second. I just draw a cleaner picture. So you have the top layer moving at a certain velocity, subsequent layers moving at slightly lower velocities. Okay, so as a result, what do you have? What is this called? The change in velocity in a particular direction. That is called as. So if I say u depends on y. I'll call this y direction. And this is what? What is the rate of change of u along y?
Velocity gradient.
Thank you. Velocity gradient. So the velocity changes because the shear stress acts on the topmost layer. Then there is an imperfect transmission of that shear stress through subsequent layers. So subsequent layers have smaller and smaller and smaller and smaller in velocity until the surface where the fluid is assumed to be stuck to the surface. So here you have zero velocity, or in other words, the fluid doesn't slip across the surface. We call it no slip. Okay, we call it no slip. So between 0 and the top layer, which is moving at u, you are having velocity form a gradient. Okay, so the main effect of shear stress is dash is to cause a it would be easier if this were elementary school. You're all adults. I can't make you do anything. So you'll have to just do it if you really want to do it. So I would really appreciate if you could talk back. You don't have to mute your mic. Just keep it unmute, talk as though this is class so that, yeah, we have some engagement.
Can you repeat the question?
The question is, if you apply shear stress, which is an action that you are taking, what is the effect or what is the response of the fluid? It develops a velocity gradient. That's the response. Because of the internal forces, the fluid develops a velocity gradient. So it's okay. I'll keep repeating this throughout the course. If shear stress is a cause, velocity gradient is a effect. Okay, it's okay. I mean, you're learning. So eventually you will internalize this, and I internalize this by saying this for 15 years. So it'll take you maybe, let's say, 3 weeks. Okay. So what is the definition or relationship between shear stress and viscosity? Tau is equal to mu du dy. Okay. So when we say we are going to consider a fluid that is subject to forces but does not experience any internal shear. Look at this. When is the situation when, what are the situations in which the shear stress can actually be zero? You don't have to externally apply it. If you just put a fluid in a bottle, and if you just spin the bottle, you are going to create some shear force. Or if you just let the water flow down, you're going to create shear force. You don't have to actually exert it externally. So my question to you is, I'll write it here. What are the situations in which the shear stress in a fluid can be zero? Can we think? So look at this equation. You want to make the left-hand side zero. When is that possible?
Whenever
Either
mu is
if mu
zero.
is 0 or
du.
du dy is constant.
Okay, so I'm going to write first zero shear stress. Okay, when is it possible? When mu, or I'll write, sorry, I have the access to the symbol here. When viscosity is zero. Okay, and then what was the other response? Du dy is?
Constant.
So when you say du dy is constant, it could still be that shear stress is okay. You are saying mu is zero, but this is constant. While du dy is some constant. Is that what you meant?
It's not that it's constant. It's that the equation that when y is in respect to u is linear is what I meant. Sorry.
Okay. I mean, I'll take the first part of this. Rashid, you had something.
Said when du is zero, but his answer made more sense to me.
Actually, I'm going to make some corrections to his answer, but let's get to it one by one. So if you look at this equation, there are three ways in which shear stress can be zero. First is you guys got it right. When mu is zero, when viscosity is negligible or non-existent, that's one way this equation is zero. The other way is that du dy is zero, that there is no velocity gradient, but there is viscosity. That is the other way it can be zero. And the third way this can be zero is when u itself is zero everywhere. That is, if u is zero, du dy is obviously zero. So it's just zero everywhere, that this whole thing is shear stress is zero. So let's write that down. The first situation is when mu is zero. The second situation is when du dy is zero. The third situation is when u is zero, or I'll say when u is identically zero everywhere. Okay. So what is the first scenario? That is, are there fluids with zero viscosity? Do you know of any?
I can't think of one.
You probably can't think of one technically, but there are many situations in which there is no real consequence of viscosity. I'll give you one example. The flow of air when no material surfaces are present. That is, if you are just having a very gentle wind, and if you don't put any tree or yourself or any structure in the path of that air, then the air will not have any resistance to flow. It will just preserve its energy, because viscosity is not something that will work unless there is a surface causing a shear force. So whenever flow of, I could even say fluid flow, it need not even be air. Fluid flow of air or water when no material surfaces are present or are nearby. Okay, that is a good situation where you can call the viscosity to be negligible because its effect is very minimal. Okay, du dy, that is the velocity gradient being zero, actually happens, for example, during rigid body motion or rotation of a fluid. If you take a cup of water or a glass of water, and you carefully spin the cup such that the entire water spins and not different parts, the whole water will rotate like a rigid body. Such, what is a rigid body? What do you know from your mechanics about rigid bodies?
A rigid body is an object with mass and shape, if I'm not mistaken.
Actually, the way you would say that, what I think what you're trying to say is, if you take a baseball, that's a rigid body, because if you mark two dots on the surface and you hit it and you play with it, the two dots will still be relatively at the same distance from each other. The molecules don't shift around, the shape doesn't change. That's what we call rigid body, right? It has a fixed shape which doesn't change regardless of what forces or stresses you subject it to. In very specific situations, fluids can behave like that the entire fluid rotates like a rigid body, meaning there is no internal motion or internal relative motion. Okay, that is one situation where shear stress can be zero, because no points are moving relative to each other, so that the du dy becomes zero. And then this is just u equal to zero everywhere. It's just a fluid at rest. That is one situation where shear stress is zero. So we are kind of going to do a force balance when shear stress is zero. That's the starting assumption. And these are the three situations in which that could be true. Okay, so now we go into the actual definition. Sorry. Okay, so we want to do a force balance, okay, on an element of fluid. What is this force balance? Okay, so let's say I have a coordinate system. I'm basically drawing figure 2.2 from the book. If I were in class, I would draw this on the whiteboard, but I'm now drawing this. So this is X, Y, Z. So you have the I cap direction, J cap, and K. Okay, we want to pick an element, basically a little cube of fluid. Okay, we want to pick a little cube of fluid, and the sides of the cube are such that it's a very small distance in each direction. This side is along the x-axis, it's delta x. This side along the y-axis is delta y, and this side along the z-axis is delta z. So the volume of the fluid will be delta v equals delta x, delta y, delta z. Are you with me so far?
Yeah, I got you.
Okay, all right, good. So we want to do a force balance, okay? And we already said no shear forces. So every phase will have only normal forces. That is, at this point X, or at this point, let's say its coordinates is X, Y, and Z. Let's say the pressure at this point is P. So if the pressure at this point is P, we want to know what is the force or the pressure acting on this this face here, which I am shading. Shade it with a different color. Sorry. Okay, I want to know what is the force on this shaded face. Any thoughts? How would we express that, knowing that we have the pressure value at the center and not at this face directly?
we're trying to find the pressure on the
shaded
ZX
face.
axis.
The shaded face is normal to the y-axis. Okay, so it's like if I travel from here towards this face, I'm traveling along the y-axis or parallel to the y-axis. So how I would write this is, so if the pressure, let's say pressure at this face, okay, we'll call it PF, just temporary nomenclature, PF, okay, pressure at this face, the shaded face, is the pressure at the center plus the rate at which the pressure changes along y, okay, multiplied by the distance I need to travel along the y direction. Would you agree? This is a very simple application of Taylor series. It is to say the pressure at a point that is close to where I know the value is the rate at which it changes multiplied by the distance traveled.
What's the original P?
So this value here, you're talking about this one?
Yeah.
So this is the value of the pressure at the center here. Let's say we talk about the pressure at a point, and at that point we take a small cube of fluid centered on XYZ.
So
That
the
makes sense?
that pressure is just the pressure in the very middle of the cube.
Yep, very middle of the cube. That's correct.
Okay.
At the very middle of the cube, it's P. So what is it on the face? That's the question. So if the face is subject to a pressure which is PF, and that PF happens to be P plus the derivative of P with respect to y, or the rate at which it varies along y multiplied by the distance along y, what would be the force on this? So if I say F, the force along the y direction on this face, that would be PF multiplied by, what is the area of this face? That would be delta X times delta Z. Look at the geometry and make sure you get this step, because after this, it's really simple if you understand this particular step. I'll give you a minute. Think about it. Let me know. Force is pressure on a surface times the area of the surface. So we assume that this PF acts uniformly on this face, the shaded face, and the force should be the pressure scaled over the area, which is delta X times delta Z. With me? Is that making sense? Yes, thank you,
Yeah, I
Nathan.
understand.
Okay, good, thank you. So this phase is PF times delta X delta Z, but PF itself is, keep remembering it, is P plus delta P, sorry, derivative of P with respect to Y times delta Y. You don't have to think too hard. If this force Fy F is this, what would be Fy on the back face? We'll call this back face. If this is to the right, if right is positive, what must be left?
Negative.
Negative, right? So let me go to the next slide. So the total force or net force along y, I'll write that as Fy should be equal to P plus partial derivative with respect to P times delta y multiplied by delta x delta z minus P minus partial derivative with respect to y delta y times delta x delta z. I just took the forward and the backward. They are both compressing the little element of fluid. So what is the net force? It must be the difference between them. If one is positive, the other has to be negative. That's all I did. Okay. So if I did that, what I'm going to get is this P is going to cancel out. Okay. And I did make one little mistake here, which is I'm at the center. If the whole length is delta y, going to the front face is going to be half the distance. And for the same reason, going to the back face will also be half the distance. But you got the sign right, plus and minus. So if I do the addition, that is the negative sign and negative sign, they become positive sign. What I'm going to get is, you can easily write, is the partial derivative with respect to y times delta x delta y delta z. Take a moment, maybe write it down and also look at it and make sure you understand it. The net force depends on the rate at which pressure changes along y. That is, net force along y depends on partial derivative of P with respect to y times the volume of the element. Christina, is it making sense?
Yes.
Yes. Okay. Brian?
Yes.
Okay, if you have any doubts or like if you're not sure, please let me know. We can talk over it. I don't want to bulldoze this through. Okay. Okay, so that was Fy. Okay, if Fy
Sorry,
is,
can we go back real quick? Sorry.
yeah,
I
sure,
just
of
wanna
course, yeah,
confirm.
sure, of
So
course, yeah,
what this equation is saying is that, are you saying that the force of y is the because you crossed out the p that we have there,
right.
or is that supposed to be x plus p plus the partial?
I mean, P times partial x partial delta x delta z minus, I'll also have another P times delta x delta z. So that's what I crossed out.
Okay.
If you multiply the delta x delta z and then do it, it'll be one more step. I just skipped it.
Okay, got it. All right,
Yeah.
no problem.
Yeah. So if I write here Fy, the net force along y due to pressure is the derivative with respect to y and then delta x delta y delta z. It's not a stretch to write what is Fx and what is Fz, because what are x, y, and z? They are just labels. They are just names. You call something y, you can call it x, or I can call it z. Nobody can, it's the same thing. We just give it different names. So the three directions are all equally likely. You can call them x, y, and z. So if you want to write out the same expression in the x direction, you don't have to go through the derivation again fully, because nothing is different in the x direction. You just replace the symbol with y with x. And if you take this expression and replace y with x and x with y, nothing will change. It will still be delta x, delta y, delta z. Same goes for z direction. Partial derivative with respect to z, delta x, delta y, delta z.
I'm gonna ask a stupid question.
No, no,
but-
no, stupid. No, don't use the word stupid. Just ask the question. Yeah.
You say delta and that is partial with respect to what?
So this is the derivative. That is when I write, where's my mouse pointer? Yeah. When I write this, this is a derivative of a function which we assume we know, like pressure is some known function of x, y, and z. So you compute the partial derivative. This is not a partial derivative. This is called a small change in x. It's like a tiny value of x. It could be like 0.1 millimeter or 0.01 millimeter, depending on what physical resolution you want to think about. But it's not a derivative in the mathematical sense.
Oh, okay.
Okay, good question. It's not stupid by any means.
Okay.
So you have this force. Okay, so if you want to write this force, as a vector, okay, because we have three components. So do we need to write it as a vector? I don't think so. We don't need to write it as a vector. We can do it without writing it. Okay, so you have these three components, right? So you think about this fluid. Okay, you've taken a little parcel of fluid and you've done a force estimation along x, y, and z. And if this is, let's say, z, and there is x, and there is y. Most often, we write that gravity, okay, if this little parcel of fluid is experiencing the force of gravity, what is gravity or weight? That is mass times g. And what is the mass of this little parcel of fluid? That would be density times its volume times g. You'd agree, right? And this is density times volume. And if we assume that g acts along the vertical, along the z direction, we'll write it g, the scalar, multiplied by k with a negative sign, because g always acts down. According to the picture I've drawn, I have to add a negative sign to denote this is gravity. Remember, we are still dealing with this very tiny volume of fluid whose volume is delta V, or I'm going to write minus rho G times delta X, delta Y, delta Z times K cap. Or if I'm hell-bent on not using vector notation, I can write this. What is the component of weight force along the x direction, along a horizontal direction? 0, right? Weight has no component along the x direction. Weight has no component along the y direction. Weight has a component along z, and that is minus rho g delta x, delta x, delta y, delta z. Okay, so this is gravity. So we are dealing with each force, gravity, and then we have pressure force, XYZ component, gravity. Nobody says gravity force, but I like to say it in this context. Gravity force. Okay. All right. Then if we have Newton's second law for this little parcel of fluid. What is Newton's second law? You recall from your mechanics courses or statics course?
F equals MA.
F equals MA. Thank you. And we have two kinds of external force, two kinds of forces. One is the pressure force that we worked out, and the other is gravity. Because we are dealing with only pressure, no shear. That's where we started. So if I take the x direction, I would write Fx due to the pressure. Gravity has no contribution in the x direction. That should be equal to mass times acceleration. And before I go further, what is mass? Density times volume, and volume being delta x, delta y, delta z. So I have, this is m or rho times delta x, delta y, delta z times the x component of acceleration. And what is Fx? We wrote that Fx is partial derivative of p with respect to x times delta x, delta y, delta z times rho ax times delta x, delta y, delta z. I keep telling you that this is a little parcel of fluid. It has a finite volume, and that volume is this, which means finite means non-zero. So I can strike out this from both sides and get an equation that is partial derivative of p with respect to x is equal to rho a x. I don't want to rush, but I also don't want to bore you by saying the same thing again and again. Is this making sense? Or am I going too slow, too fast? Thank you, Nathaniel. Nathaniel,
I like this pace.
Yeah, I'm good.
thank you. Thank you. Thank you. Appreciate the feedback. Okay. So if along the x direction we wrote this, is there any difference between x and y? Or in other words, if I call x direction as y and y direction x, is there any material change here? No. It's just a way of calling things, right? Thank you. So which means the y equation, I don't have to sweat. I can just take the x equation and change the symbol and generate one more equation. And this is the trick you should kind of understand so that you can save a lot of effort later. You should understand symmetry. All right. Z direction, partial p with respect to z equal to, of course, I'll have rho z, but along z direction, I also have to include one more force, which is
Gravity.
gravity. And gravity has a form. So I need to move all this to the right. Gravity has a form like minus rho g plus. There is gravity is pointing down. That's what this minus denotes. And then there is the pressure force, pressure gradient or pressure variation with respect to height or z must be equal to rho times az. Okay. So if I put them together just for sake of clarity, I'll bring the x equation here so you can have them all in one place. Partial p over partial x equal to rho times ax. Here is it. If you have a fluid in which there are no shear forces, the pressure distribution is described by this set of equations along x, y, and z. The main restriction is no shear. Make sure if that assumption is okay, then you can use this equation to describe what is the pressure distribution in that fluid. When I say pressure distribution, I know what I'm talking about. What do you understand? What is that word pressure distribution or pressure field denote for you? Please tell me in simple words that you can. Pressure distribution or pressure field. Can you please tell me what you understand?
Does it just kind of describe the pressure along all the area of the parcel?
I think what you mean is along all the points that are within that parcel, not area, points,
Sure.
like from point to point. Yeah. The way pressure changes in all the directions. All the directions are basically throughout the space. So if you think of that continuous space of X, Y, and Z values, how does pressure change from each point to point? That's what distribution or field means. Okay. So let's tidy this up a little bit. For those who are into vector notation, I can write that here. Pressure field in vector notation. So that would be, I can write the operator called gradient of P is defined as partial derivative of P with, actually I'll do this with equation tool where I can do it much faster. All right. So gradient of P is the partial derivative of X of P with respect to X along the I direction plus the derivative with respect to Y in the J direction, which is the unit vector for the Y direction, plus P with respect to Z along the K direction. So this quantity is called pressure gradient. Pressure gradient, which is a vector, vector. And we have the force of gravity or weight that is given by, oops. So if you want to have it in the same notation, that would be, what's the component of gravity along I? 0. What's the component of gravity along J? That's 0. And what's the component along K? That would be G times the density, and I add a negative sign to denote its downwards. We'll give it a symbol. We'll call it FG. Oops, sorry. FG. Okay. FG. Okay. And then we have to write mass times acceleration. So we can write M A mass times acceleration is equal to the pressure gradient minus rho G times K. So this is the vector equation for pressure field. It is P as a function of X, Y, and Z. If you solve this differential equation or vector differential equation, you can get pressure. And we'll do this for highly simplified situations. We won't turn this into a mathematics class and make you solve very difficult equations, but we'll try to use this concept in simplified situations. Okay. So this is given as equation 2.2 in the book. I should write not MA, it should be rho A, because we already cancelled out the area, which is area of that little parcel of fluid. So this is the equation you want to use to solve problems. If you understand this equation and you can use it in any context, every context is just a subset of this situation, of this particular equation. Okay. So I'll say add some notes here. Every context is a subset where we simplify this equation by dropping one or more terms to make it easily solvable. Okay. Are we okay? Are we together? Nobody's lost. Thank you. Okay. All right. The first application of this equation is section 2.3, fluid at rest. What that automatically means is if it's at rest, it's not accelerating or moving. So its acceleration is 0. So you have, I'll take this equation and start here. So all problems start kind of like you have one basic equation. You should be able to write that down first in its most general form. Apply the assumption or the simplification. If it's a fluid at rest, okay, it means A is 0, and that leads to gradient of P equal to 0. Okay, if gradient of P is 0, how many equations are actually packed into this vector notation? Is it just one equation or more than one? Vector notation is a compact shorthand for expressing what goes on along 3 directions or 3 components. So this is not just along, it's not just one equation. It actually splits into 3, which are essentially these 3 equations. Okay, so if I write gradient of P minus rho g times k unit vector k is equal to 0, this is like writing the partial derivative of P with respect to x is 0. What does that mean? It means P is a function of y and z only. Your calculus, basically, if the partial derivative along some variable is 0, what is that saying? It means P doesn't depend on x, which means P depends on y and z only, right? Do you agree or do you see that?
Yes.
Yes. Okay. Same argument applies for the y direction also. So whatever I said about x, I can also say about y. If partial derivative of P with respect to y is 0, it means P depends on z only. So suddenly this pressure, which we thought is a function of x, y, and z, is now only a function of z. It's varying only along gravity, where there is a force that's influencing the fluid. So then if I write the third equation, partial derivative of P with respect to z, of course, that's not 0, minus rho times g, sorry, minus rho times g equal to 0. Okay, let's see here. What did I miss? So why is there a sign mismatch here? One second. I need to check if I made some sign mismatch here. So this is Fy forward. Okay. I apologize, folks. I kind of got the sign backwards. So let's see here. So if Fy is pointed this way, according to this coordinate system, Fy forward or Fy on this face must be a negative force. And if Fy backward is faced this way, according to this system, it must be a positive force. Would you agree?
Yeah.
Yeah, right. It's consistent with the way we express this coordinate system. But in the next slide, when I did the difference, I wrote this as positive, whereas this must have been negative. So I should have added a negative sign. And this is positive, but I added a negative side. I should have made it positive. So I should have had a negative sign all along. Okay. So when I wrote this equation, I should have had a negative sign, a negative sign. So I should write this as negative sign. Sorry. Okay. So this is the equation. It has a negative sign minus rho A. Yeah, that is consistent with equation 2.2. Rho A equal to negative gradient of P minus rho G times unit vector K. And when I simplify this, I will get minus for this X and Y direction, it didn't make a difference. Okay. And for Z direction, if I add that difference, what am I going to get? dP over dz equal to minus density of the fluid at Z, okay, times G. I apologize, but is it making sense what I did and why that is the sign had to be reversed? Okay. All right. So what is the consequence of this equation? Just look at it, think about it for a second, and tell me what comes to mind. It says the rate at which pressure changes along the vertical direction or the direction in which gravity acts is equal to rho times G. What does it mean? So here is Z direction. It's pointed upwards. Here is gravity pointing downwards. Okay. Look at this equation and interpret it in words for me. Yes, Isaac, you are going to say something.
I was going to say, basically it means that the change in pressure in the Z direction is just your density multiplied by your gravity. So you, I mean, it's.
Let me take your answer and help you make it more precise. You said change in pressure, right? If you look at this equation for a second, if you just think of density of the fluid and G, both are positive numbers and there is a negative sign, it can only mean the pressure will decrease as you go higher. If you go along Z, if you go in direction of increasing Z, the pressure has to decrease. That's what the statement means.
Okay.
Okay. So the first thing you want to write down is this equation says pressure will decrease along the direction of increasing Z. The pressure will decrease along the direction of increasing height, okay, Z, that is the direction opposite to gravity. That is, if you walk or if you go up opposing gravity, pressure will decrease. Is that relatable? Is there anywhere that you have felt that you are climbing higher and pressure feels lower? Is that something any of you experienced in real life?
Yeah. I mean, the first example I think of is like the Ocean 4, for instance.
You're talking about going down or going up?
I guess going down.
Okay,
Which would
if
just be,
which will be the corollary of this. If it will
Yeah.
decrease, you can also state this as pressure P will increase along the direction of decreasing Z, which is okay. So you're saying if you went down, took a dive into the ocean, pressure will squeeze you harder as you go further and further. Any other experiences in real life which confirms this statement?
So I've been hiking on like some mountains. The one like most recognizable is I guess is Red Mountain 3. Going up to those elevations, you don't necessarily feel lighter, but you can definitely feel the air thin around you.
So what's the elevation in feet typically?
I believe it is 13,000 feet at the top of Red Mountain 3.
Okay, you don't feel lighter, but you feel lightheaded. Is that okay to say?
I wouldn't say lightheaded, but you can feel the air thinning.
Okay, so you can feel the air thinning, or you can see the pressure being lesser than at sea level. Any other experiences people have had? Going up and feeling that the pressure is lower or the air is thinner? Hot air balloons, anybody? Have you tried? No? Okay. I've been to Himalayas, or actually one part of Himalaya. It's called Ladakh. It's the world's tallest mountain pass at around 18,500 feet. And when I went there, the army people who are stationed there, they said no civilians can stay here for more than 20 minutes. It's not a rule. It's basically something that you feel lightheaded literally if you stay there for longer, because the pressure is so low that it actually makes people pass out sometimes, or they get disoriented. So that's because pressure decreases if you go higher in altitude, and that's precisely coming from this relation. Pressure has to decrease in proportion to the density and gravity as you go higher.
You could say on an airplane when your ears pop because of the high pressure.
Thank you. Because of low pressure.
Yeah.
That is your internal pressure will be higher, but the outer pressure has suddenly changed. Good. Yeah. Yeah. Anybody wants to say something before we move on? You can do a lot of math. You are going to do a lot of math, but remember this intuitively. If you identify the direction in which gravity is acting, pressure decreases if you walk opposite to gravity. Pressure increases if you walk along gravity. Just remember this statement. It's the difference between going up in a hot air balloon or putting on a scuba diving suit and taking it, jumping into the ocean. Make sense? Yes.
Yeah.
Okay. What I like to do when I was a student, and even now when I'm teaching, is that it's not the fancy math and the equations that you should master. It's the ability to read an equation and say the meaning in words. That's what matters. It's not that you can solve it or not you can solve it. It's that can you interpret it. Okay. All right. Good. So now we want to talk about some specific fluids. Let's talk about an incompressible fluid, which is commonly liquids, incompressible fluids, which are commonly liquids. or gases at very low velocities. Okay. What is an incompressible fluid? I think we talked about a little on Tuesday. What is being incompressible means? Incompressible means
Its volume does not change with pressure.
the volume, exactly. The volume does not or cannot be changed by applying more compression or pressure, or in other words, the density rho is independent of pressure P. So it's like saying rho is just a number, a constant, which comes from the material's internal molecular structures and interactions. It's not related to the external pressure that you impose. Density is rho is a constant. Yeah, which means if you take the equation that we just wrote, derivative of P with respect to Z is minus rho times G, then the integration becomes really straightforward. The pressure difference between two heights, Z2 minus Z1, is simply equal to minus rho G times Z2 minus Z1. All I did was integration from Z1 to Z2. So if I have my coordinate system, X, Y, and Z, and let's say I pick two datums or two heights. One is at Z1, one is at Z2. The pressure difference between the 2 points is simply equal to the density times G times the height difference. And now that it kicks in, whether if I am going, if Z2 minus Z1 is positive, meaning I went up from Z1 to Z2, this would be a negative change, meaning the pressure difference between the top point and the bottom point is negative, meaning the top point is at a lower pressure. If I went down, if my Z2 is over here, if Z2 minus Z1 is a negative number, which means the pressure went up, which means I went along the direction of gravity. So it's kind of intuitive if you think about it in reference to, am I opposing gravity or am I going along with gravity? Okay. All right. So we want to introduce some terminology here. All right. That is commonly used. That's why I'm introducing it. Pressure difference is commonly denoted as delta P, and that could be the pressure difference between 2 points which differ in height. Okay, and we'll write delta P is equal to minus rho G times, I'll write H. Okay, then there is height difference. H is equal to Z2 minus Z1. So we write the change in pressure is equal to the difference in height between two levels along the vertical direction. And we also define pressure head H, okay, as H equal to the pressure drop delta P divided by rho times G. Pressure drop divided by rho times G. Can we talk a little bit about where are situations in which we don't express pressure in units of Pascal or any other system, but we talk about pressure as though it is a distance, as though it's a height of something. Of course, we're going to define it more carefully, but in your life, where all do you talk about pressure head in height terms?
Well, this
Yeah.
is kind of yes and no. I believe bar is a unit of measure originally designed for tanks of water, where every bar is 10 meters of water.
I see.
I believe that's correct. I could be totally wrong on that.
So let's do a quick check. You say 1 bar is, your conversion is 1 bar is 10 meters of water, right?
Yes.
So the way you convert a pressure head into an actual pressure is you take the density, you multiply by gravity, and then you multiply by the height. So even if we approximate this by 10, I think you might be onto something there. This is 1 bar. This is 10 power 5 Pascal, or defined as 1 bar. So it might not be 10 meters, maybe it's like 9.81 meters, maybe. But the idea is that it's probably 10 meters. I think that makes sense. Where else do you talk about pressure as height? Yes.
I think millimeters of mercury, I think, is another one.
Yes. So if we go to the doctors and they take our blood pressure, they talk about 120 millimeters and then 80 millimeters. They're referring to a mercury column of height 120 mm and 80 mm. Okay. So the other example is blood pressure. The famous 120/80 measured in millimeter of mercury. Where else? How many of you are somewhat familiar with farms, agriculture, dam, and water release from dams by local state governments or TVA, where they report the dam's height today is 140 meters, 130 meters, stuff like that? Okay, even I'm not very familiar, but what I do know is they never report the pressure level. The only thing that they report in about dams is the height. If you know the area, you can convert that into volume. If you know the height, you can convert that into a pressure distribution on the sluice gates or the walls. Where one more example, and then we'll move on. Pressure head. So here's something you should do. Next time, if a plumber visits your house to fix anything, ask them, what is the typical pressure of water when it enters the house? Or you can check the water meter and see what units they use. Odds are they probably will not use Pascal. Maybe they're using some unit which is a measure of length of water column or height of water column. Okay, so check utility water pressure. Okay. All right. We'll do some problems on this, especially the pressure distribution on incompressible fluids. But I also want to talk about compressible fluids. As we talked about incompressible, what is a compressible fluid? What's the contrast? So here pressure does not depend on, or pressure is decoupled from density. What is a compressible fluid? It allows for volume change, meaning its density can be changed or increased by applying larger compression. Okay. And for a gas, especially, we use ideal gas model or ideal gas law to describe the density or describe the relation between density and pressure at high temperature, low pressure situations. And you know what ideal gas law is? P equals, or rho equals P divided by RT. Rho equals P divided by RT, where R is called the universal gas constant. I'm not too worried about the what value of that R. When we do problems, we'll pick the right value. But for now, just think that R is a constant whose value is the same for every gas, whether it's nitrogen, helium, argon, oxygen, whatever. More importantly, ideal gas law specifies a relationship between density and pressure. It tells you density will increase if pressure increases. It also tells you density will double or increase by the same factor by which pressure is being increased at constant temperature. So it's a very definitive relation between linear relation between density and pressure. So if you have a fluid in which, let's say it's a room, let's say it's a mega factory whose height is like 150 feet. And if you have a elevator that can go from ground level to all the way to the top to 140 feet or something, what would be the change in pressure over that 140 feet? That's the question. Okay. So we would think dP over dz is minus rho times G, or minus P divided by RT times G. Are you with me? Yes?
Yeah.
Yes? Okay. So if I do the same integration, that is between two points, or if I just take this schematic and say, I want to know what's the pressure difference between 2 points which are separated by some height Z1 minus Z2. I haven't told what Z1, Z2 are. In my example, Z1 can be 0 feet at the ground level. Z2 can be 140 feet at near the top of that mega factory. So P at Z, sorry. If I were to integrate this, I would write dP over P is equal to minus G divided by RT times dz. I'm just separating them as a differential equation. And then I have to integrate this between, let's say, pressure at Z1 to pressure at Z2 dP over P, that is equal to minus G over RT. We'll assume temperature is not changing. That will be a simplification. Integral of dz, which is like Z2 minus Z1. T naught, so that we know it's a constant, not a variable. Okay, so then you can write the next step, which is the pressure at Z2 over pressure at Z1. Okay, this must be equal to the exponent of this term here. I kind of wrote that just to save time, but tell me if that makes sense, because all I did was to integrate dp over p, where I'll get natural log of p, and I turned the natural log to the other side to convert it into an exponential function. So P2 or P pressure at Z2 over the pressure at Z1 is equal to an exponential function of the height difference, or I can write P2 is P1 times an exponential function. I'm going to stop here, but quickly, in the case of incompressible fluid, the pressure difference is linear. In the case of compressible fluid, the pressure ratio is exponentially changing. So if you go very far up, the pressure will quickly drop to zero, or the pressure difference will quickly drop to zero. Okay. So this is the main difference between compressible and incompressible fluid. Here it is linear with height. Here it is exponential with height. Okay, so this is essentially comes down to dealing with how do you calculate pressure changes in liquids, which are incompressible, and air, which is a compressible fluid. That's the main application of these two principles here. Okay, so everything that I've discussed so far is up to section 2.3 of the book, which I would strongly encourage you to go through. And hopefully next lecture we will also do some problems and problems related to what I've done so far before adding more topics. Okay, so we'll do problems until this point, at least the first half of next lecture. Before I go, any questions? Okay, so we'll meet on Tuesday. Let's hope we'll be in campus. Thank you.
Goodbye.
Thank you.
Have a
Goodbye.
good one.
Thank you. Bye.